Alright, welcome back. In this video, we're going to go over the citric acid cycle step 4, the easiest on YouTube. Now, before we begin, something crazy has happened. I gained 600 subscribers in the past 48 hours. What the shit? Has it been 10 seconds? Yeah, it has. Shit! This is fucking amazing. Thank you so much for the support. I guess the last video, the easiest citric acid cycle video I made, right, part 1, did amazing because you look at this, 2.5 thousand views. I'm speechless. Amazing watch time. Thank you so much. We're over 1,000 subscribers. That's incredible. Dream come true. So let's begin the step 4 of the easiest citric acid cycle on YouTube. So we ended okay, I gotta say this. If you have not watched last video, you should really watch it because we're on step 4. Why would you watch this on step 4 if you haven't watched step 1, 2, and 3? So please watch that. So step 4. We ended step 3 with alpha ketoglutarate. Here's what's gonna happen. Looks complicated, it isn't. This is gonna be a reoccurring theme. Every single step from here on out looks complicated, but I promise you it's really easy. It's really simple. I'm going to make it simple for you guys. Here's what's going to happen. This alpha ketoglutarate has 1, 2, 3, 4, 5 carbons. The 5th carbon and all the oxygens attached to it are going to leave. They're going to go bye-bye. They're going to be excreted as CO2, right? Because we have 1 carbon here and 2 oxygens. That is CO2. We're going to exhale that. What we're going to do is we'll replace it with a sulfur group and a coenzyme A. This is called succinyl CoA. So this enzyme here with the sulfur group is going to be wandering around. It's going to come along and basically replace it. Right, it's going to replace this carbon, oxygen here. At the same time, we are going to reduce NADH. So notice that here we have coenzyme A and a sulfur group and a hydrogen here. This part goes on the molecule. This part goes here to reduce the NAD+. And remember, I talked about in the first video that NADH is an energy carrier. So we just banked in some energy, cha-ching, and this is going to go to the electron transport chain later. And the enzyme we use is alpha ketoglutarate dehydrogenase. So this entire reaction is called oxidative decarboxylation, right? Oxygen, and it's decarboxylation. This is a carbon. We're decarboxylating. We're removing a carbon. That's what decarboxylation is. And that's it for step 4. So once again, all we're just really doing is replacing this carbon, oxygen here with sulfur and the coenzyme A, making succinyl CoA, and at the same time reducing NAD+ to NADH using the enzyme alpha ketoglutarate dehydrogenase. Step 5 is probably the easiest one. Here's what we're going to do. This is kind of weird to think about, but I'm going to explain why we're doing this. We just made the succinyl CoA. What we're going to do is literally take this out. So you're probably wondering, why would you do this? There's actually a really good reason. So let me explain what we're doing first. We're going to take this succinyl CoA and we're going to replace it with a phosphate group. And it becomes actually an acyl phosphate. This is an acyl group with a phosphate. And we're going to use the enzyme succinyl CoA synthase. And since we're removing this, plus there's an invisible hydrogen here, that's what we're going to leave out. That's what goes bye-bye. And we're basically just replacing it with a phosphate group, making a succinyl phosphate. Okay? This releases mega amount of energy. Negative 32.6 kilojoules per mole. That's insane. That's a lot of energy. Why are we doing this? We're doing this because the very next reaction that we have, step 6, costs a lot of energy. And since it costs a lot of energy, it would not want to move forward, right? Why would we, if something costs energy in your body, why would you want to do it? So we need this reaction to release a lot of energy to couple the next reaction so it can drive it forward and make it happen. That's the only purpose of this step 5, is to make sure that next step happens, because the next step costs energy, mega amount of energy. That's why we're doing this. Okay, so the enzyme succinyl-CoA synthase is involved in this step and the next step. All right, so once again, all we're just doing is replacing the sulfur with the coenzyme A with a phosphate group. And we just basically just added a acyl phosphate. That's it. Step 6. This looks complicated. I know. I drew it differently because I think it's easier for you to understand, but it's, once again, quite simple. Ignore the writing first. Let me explain what's happening. So we have the succinyl phosphate that we just have, right? A random histidine residue that's wandering around in the body, in the mitochondria, is going to come along. It's going to basically say, hey, I see you have a phosphate group, let me take care of it, and I'll move it to where it needs to go. So what's going to happen is the histidine residue, yes, it is going to pick up this phosphate group, okay? It's going to pick it up. Actually, it's going to put it right here, okay? So now we have this phosphohistidine residue here. And in return, since we just eliminated the phosphate group, we have left one oxygen on there, and this becomes succinate. You'll notice there's also a hydrogen here. This hydrogen is coming from here. So this hydrogen gets released because we need to bond the phosphate group. Okay? So we just basically have some bonds going around, moving around. So now we have this phosphohistidine residue here. Okay. Now what we need to do is make energy, right? We need to cash this in, put a deposit down. How are we going to do that? There's going to be a random GDP molecule floating around. This GDP is like ATP but guanine based. You'll notice this inorganic phosphate. This is the same thing as this. It's the same thing. Okay? What's going to happen is this is going to break off and it's going to join GDP to make GTP. Okay? Doing so will regenerate this histidine residue, which would go back here to be reused. This holding energy costs a lot of energy, right? This holding this phosphate group, and this is like packed with energy, it's holding a lot of energy. This whole thing costs energy to run. So that's why we had this reaction. Notice that negative 32.6 kilojoules and positive 30.5 kilojoules. If you do the math, we're still negative, and that is why we move forward. If this was positive, if the outcome, if the net reaction, the net energy here was positive, we would be stuck. Our body would not make this happen. We would be stuck right here. But since we're negative, right, we have negative 32.6 kilojoules when you do the math, right, when you do this plus 30.5, whatever it was, we're still in the negative. It's a net negative, so we still move forward. So this is called substrate level phosphorylation. So once again, this entire reaction costs energy, but it's driven forward from the last reaction. Okay? And that is basically it. So we're now left with succinate, which would go on to the next step. And now we have this GTP that's going to be used for later on the electron transport chain. So we just cashed in. We just went to the bank and we just made a deposit. Cha-ching! And we love that. That's what we like. So that's the end here for step 6. I'll do the rest. I'll probably finish off Krebs cycle in the next video. Once again, thank you so much for the support. Please like and subscribe. And until next time, later.